Set notations. For a set, we use capital letters like A, capital letter B, C, D to denote a set. While we use small letters like this to denote the elements. A particular set is defined by listing its members. For example, we can say set A having A, B, C, and D as its element. So this particular set A is defined by listing all its members. The members of this set A is A, B, C, D. This form of a set where the element is separated by comma is called tabular form of a set. It's called tabular form of a set. This form is called a tabular form of a set. Why we define a set by enclosing a rule within the braces that determines the elements of that set. We call that one set builder form of a set. We call that one set builder form of a set. Example of this set builder form of a set, let's say set B X, such that this two dot means such that X is even numbers. Now, this is set builder form of a set. This type now. The way we list this thing with this rule, this is the rule enclosed by these two braces. Means this rule means all the numbers that is even is under set what? Is inside set B. So this form is called set builder form, while this form is called tabular form of a set. Another thing you need to know under here is when we say A, when we write A with this, it means that A is an element of set A, or we can say C with this. It still means C is the element of set A. But when we write something like this, it means that E is not an element of set A. So this means element, while this means is not an element, not element. Why this one is the element of what? Set A. Why this one is talking about not element. Cardinality of a set. Cardinality of a set is the number of elements inside the set. And cardinality of a set is noted as this. We use this to denote cardinality of a set. Now, this thing means cardinality of a set A. This A means set A, while N means number of elements inside set A. Let's take an example. We say A, we say 2, 4, 7, 9, let's say 8. Now, the cardinality of this set, now is equal to 5, due to the number of elements inside the set A is 5. We can take another example. Let's say B X, such that 2 is less than X is less than 4, where X is an element of R. I hope you remember what is R, real number. Now in this, 2 is less than X, X is less than 4. This is also a set builder form of a set. So 2 is less than 4, 2 is less than X, X is less than 4, where X comes from real number. The cardinality of set B, here is infinity, because you cannot mention the numbers between 2 to 4 under the rule of real numbers, because we have fractions. Even the range of number between 2 and 3 is infinity, because you have to mention all the fractions between them, and their fractions has no end. You can have 2.1, 2.10, 2.100, 2.9999999, and you can never enter what? 3. So the cardinality of this set now is what? Infinity. Finite and infinite of a set. A set is finite when the number of elements, or let's say the cardinality of that set, is countable. A set is finite when the number of elements inside that set is countable, or the cardinality of that set is countable. Example, let's say a set A, let's still use 2, 4, 7, 9, 6. Now, this is a finite what? Set, because the cardinality of set A is equals to 5 here. So is what? Countable. But for infinite of a set, let's see set B. Set B, let's say dot, 3, 5, dot. This means that set B is infinite. It doesn't have any beginning, and it doesn't have any what? End. So set B is infinite, while set A is finite. Also, this type of a set is also infinite. Something like this is also finite. So this one has a beginning, but it doesn't have an end. So you cannot mention the cardinality of these two sets. Even if you ask the cardinality of the set, the cardinality is infinity. That is uncountable. Sorry, this is not A, it's B. So the cardinality of this C is also infinity, is uncountable. This is all about finite and infinite of a set. Singleton set. A set is singleton when it has only one element. Example, we can say set A having A. This is a singleton set. We can also say set B X such that 2 is less than X and X is less than 4, where X is an element of integer. Now this is a singleton set. Why is it this a singleton set? Look at the range of numbers. They gave a range of number that 2 is less than X, which means X cannot be 2, and X is less than 4. Therefore, our set B, the element of our set B under integers, is only 3. So set B is also a singleton. Null or empty set. A set is empty if it has no element. A set is empty, or we can call it a null set or empty set when it has no element. Example, let's say set C A such that 4 is less than A and A is less than 6 and A is even. A is even. Now on this set, C is equals to a null set. C is an empty set because the number between these two range is 5 and 5 is not even. 5 is odd. Therefore, C is an empty set. We use this symbol, this one, as empty set, or we use this symbol as sign for what? Empty set. Either this or this. Don't use this. This is not empty set. This is not empty set. Rather, this is a singleton set containing an element called what? 0. This is not empty but a singleton set. Universal set is a set that contains all the elements under a discussion. So, example of a universal set, let's use our country, Nigeria. Nigeria is a universal set containing all the states in Nigeria. Are you seeing it? Now, these states, they are set on their own, containing towns inside each and every one of them. Inside each state, they have their own town, local government, containing it inside that particular set. But this is a universal set containing the whole set. And the universal set, we use this to denote the universal set, or this. Or this. So we use these two to denote universal set. Let me give a small example on this universal set. Let's say this universal set is a set containing 1, 2, 3, ... 10. Remember, this is not an infinite set. It is finite. It has an end, 10. So let's see other sets now. Now, this is a universal set. We can have set A. We have set B. Now, this is a set on their own. This is a set on their own. But two of them, this universal set covers the two. So this is a universal set. So all these sets now, they are inside the universal set. Equality of a set. Two sets are said to be equal if they contain exactly the same element. For example, if set A contains A, B, C, D, and set B contains B, C, D, A, we can say that set A is equal to set B. The order of elements is not important here. We are not considering which one comes first, but since the same element is here, the same element that is here is the same element that is here. So set A and set B are said to be what? Equal. Subset. Let two elements, let A and B be two sets. Be two sets. If all the elements in A, all the elements in A is inside the element of B, then A is a subset of B. For example, let's take A to be a set of 2, 5, 7. Let's take B to be a set of 1, 2, 5, 6, 7. Now, you can see that all the elements in A is inside B. So we can say A is an element of, A is a subset of B. A is a subset of B. We use this to denote subset. Why we use this? To denote not a subset. So if we write something like this, it means that this is not a subset of this. Okay, let's introduce a set C. Okay, let us not use C. Let's introduce a set D. Let's say that set D is 1, 5, 4, 3, 2. Now we can say that D is not a subset. It's not a subset of B. Why is it not a subset? 4 is here, there is no 4 here. 3 is here, there is no 3 here. So D is not inside what? B, but A is inside B. This natural number is a subset of whole number. Is a subset of whole number. Remember that all the numbers in natural numbers starting from 1 to positive infinity, all of them are whole numbers. Now, whole number has one thing different from natural number. Whole number contains 0, but natural number starts from 1, but whole number starts from 0 to positive infinity. Now, this whole number is a subset. Of integers. Is a subset of integers. This whole number is a subset of integers. Remember that integers are whole numbers. The difference is that integers has negative and positive whole numbers. Now, this integer, let's say, is a subset. Let's say is a subset of rational number. This integer is a subset of rational numbers. And also remember that this integer is also a subset of a rational number. We can say this integer is also a subset of irrational numbers. We can do it like this, irrational numbers. Now, These two are subsets of R. These two are subsets of R. Now, R is a subset of complex number. Is a subset of complex number. This is how B goes. From natural number is a subset of whole number. Whole number is a subset of integer. Integer is a subset of both rational and irrational number. Now, rational and irrational number is a subset of real number. Real number is a subset of complex number. Comparability. Two sets are said to be comparable if, let's say, set A and B. So two sets A and B are said to be comparable if set A is an element, if set A is a subset of B and B is also a subset of A, then we said that the two sets are comparable. So this is for comparability of two sets. Note, every set is a subset of itself. Null set is a subset of all the sets of any set. Null set is a subset of any set. Now, a set can be a subset of its what? Self. These two subset now is called improper subset. Like if you have A, let's define A as a set of A, B, and C. We can say that A is a subset of A. A is a subset of itself. And we can also say that empty is a subset. That is, null set is a subset of what? A. These two types of subset are called improper subset. Power set. Power set is a set that contains all the subsets of a given set. Let's take an example. Set A containing 1, 2, 3. Now, let's list the subset of this set, because we know that the power set is defined as the set of all the subsets of a given set. So we have a given set A. Let's list out the power set. And we use this to denote power set. We use this. This means power set of set A. So let's say power set of set A. You say is a set. First one is a null set. We know that null set is a subset of all the sets. We can take this one. Another one is this. Another one is 3. We have this 1, 2, 3 is the set itself, because remember we said that a set A is also a subset of its set. We close it. Now, this is power set of set A, Remember, we said that power set is a set containing all the subset of a given set. So there is a formula we use to calculate this to know how many number of subset a set have. So it will be easy for us to list it. Now in this formula for power set, we can say is 2 raised to power n. Some people will write a. Some people will write a. Some people will write n. This n means the cardinality of that set. The cardinality of that set. Now let's use this. 2 raised to power n. The cardinality of this set is what? 3. So we now have 2 raised to power 3. And 2 raised to power 3 will give us 8. It means that this set has 8 subsets. Let's count it. We have 1, 2, 3, 4, 5, 6, 7, 8. So you can see that this is the formula we can use to find the number of subsets a set has. When you have this number, it will not be easy for you to list those things. Now, if anyone is missing, it must be accurate with this number. If anyone is missing, you can easily go back and check the one that you skip. So this is all for power set. Equivalent set. If two sets A and B contains the same number of elements, then we can say that set A is equivalent to set B, but they are not what? Equal. Some equivalent sets can be equivalent. Let me put it like this. Equal sets are equivalent, but not all equivalent sets are equal sets. Let's see. Let's say a set A to be 1, 2, 3. Set B 7, 8, 9. Set A is equivalent to set B. Set A is equivalent to set B. We use it to denote equivalence. So set A is equivalent to set B because they contain the same number of elements. The number of elements here is 3. The number of elements here is also 3. So A and B are equivalent. So in this place, a set A can be equal to set B and also be what? Equivalent. But not all equivalent sets are equal. Example is this. Is not both of them are equivalent, but they are not equal. But for a set to be equal, it will be also what? Equivalent what? Set. Set operations. Under set operation, we have union. The union of two sets, A and B, is noted by, let's say, union of two sets A and B is noted by this. We use this symbol to show union of two what? Set. Union of two sets. We use this to show union of two sets. Now, union of two sets, we can define union of two sets as union of two sets A and B. We can define it as X such that X is an element of set A or X is an element of set B. So this is definition of union. Union of two sets means combination or combining the elements of the two sets without repetition. combining the elements of the two sets together without repetition. Let's take an example. Let's say set A is 1, 3, 5. Now let's say set B is 2, 5, 7. The union of A and B will now be 1, 2, 3, 5, 7. We combine the two elements together without repetition. What we mean by without repetition, you can see 5, 5, but we only choose what? 5. So this is union of two sets. Another thing you need to know on this union, that A is a subset of A union B. Also, B is a subset of A union B. Two of them, whenever the union of two sets, each one is a subset of that union. You can see that A is a subset of this and B is a subset of this. And we use this to represent it on a Venn diagram. Let's draw the Venn diagram here. Venn diagram. This is how we represent union of two sets. Union of two sets. A, union B. This one is our A. This is our B. Now the Venn diagram means all the sets. So we shed everything. Everything. So this is a Venn diagram of A union B. Intersection of two sets A and B is denoted as this. We use this to denote intersection of two sets. Let's define it. A intersection B is a set, let's say X, such that this X now, such that X is in A and X is in B. This means that the element inside A that is also inside B. The element that is inside A that is also what? Inside B. Let's take a physical example. Let's say that A is 1, 2, 3. I'm using three numbers, so this video will not accumulate much time. B, let's say 3, 5, 7. Now, the intersection of A intersection B is given by 3. Now, here, A intersection B is a singleton set because it has only one element. So, you can see this intersection means the element that is in A that is also in what? In B, which is 3. And note that intersection A and B is a subset of A, and intersection A and B is also a subset of B, because you can see this inside this, you can also see it inside here. Let's look for the Venn diagram. This is how to draw the Venn diagram of intersection A intersection B. This is how to draw the Venn diagram, where this is our A and this is our B. The intersection is here. This place is the intersection. If A intersection B is equal to a null set, it means that A and B has no element in common. And we can represent this in a Venn diagram. We can represent this in a Venn diagram. This is A and this is B. So A and B, they have nothing in common. Another thing about this Venn diagram, some textbook can put their A inside and B inside as this, but you can also put it here to note that this is this and this is it, assuming if you want to shade the inside. So this is the Venn diagram. Let's put it inside since we are not shading. So this is the intersection of A and B that is a null set. A intersection B that gives us a null set means that A, that is means set A and set B are disjoint. Set A and set B are disjoint. From the Venn diagram, you can see they are not joining, so they are disjoint. Complement of a set. Complement of a set are those elements that is in a universal set, but not inside a given set. And we use this to denote a complement of a set. Let's say this. We use this or this. So this means complement of set A. Let's take a universal set to be 1, 2, 3, 4, and 5. Let's stop here. Now let's take set A to be 2, 4, 5. Complement of set A now will be, complement of set A will now be 1, 3. Complement of set A is 1 and what? 3. Now you can see that this is a universal set given. This is a set A. The complement of A are those elements inside the universal set that is not inside set A. Another thing you need to know, a set, the union of a set and its complement will give you a universal set. The union of a set with its complement will give you a universal set. If you take the union of these two, you will get back this. The intersection of a set with its complement will give you a null set. The Venn diagram of a complement of a set is drawn like this. Let's draw the Venn diagram. Now here is the universal set. Now let's say this is our set A. The complement of set A are those places that is not inside a set that are not inside the set. This is the Venn diagram for complement of a set what? A. Difference of two sets. Difference of two sets is noted as this. This means all the elements in A that is not in B. All the elements in A, some people will say all the elements in A minus the element in B. We can define the difference of two sets by saying A x such that x is an element in A, x is not an element, is not an element in B. Those set that is in those elements that are in A but not in B are called difference of what? Two sets. Are called difference of two sets. Let's give an example of those sets. Let's give an example. Let's use numbers, or let me use alphabet. Let's say A, B, C, D. Let me use only 4. Then set B is C, A, E, F. Now A difference B will now give us the elements in A but not in what? In B are B and what? D. This is difference of two sets. We can represent it on a Venn diagram this way. We can represent it on a Venn diagram this way. A and B. Here is A and here is what? B. We will now shade here because it is only A minus B. It is only A minus B. We cannot shade here because if you are shading here, some part of B is inside here. So it's only A minus B. So this is a Venn diagram of A difference B. Another one is symmetric. Symmetric difference of two sets. Symmetric difference of two sets. We use this to denote it. This is a sign of symmetric difference. We define a symmetric difference as with this, let's say x, such that x is an element in A, x is an element in B, x is not an element in A intersection B. This is the definition of symmetric difference of two sets. Let's take an example. We have A to be A, B, C, and D. Let's take B to be C, D, E, F. The symmetric difference of A and B will now be all these elements in A and B, but not in their intersection, which is A, B, E, F. This is a symmetric difference. Now we can draw a Venn diagram for symmetric difference. The symmetric difference, we can draw a Venn diagram. Here is A, here is B. So it's all those ones that is not in the intersection. Here, but in the intersection is not included. So this is a Venn diagram for symmetric difference of two sets. Yeah.